Namaste students, welcome back to Rama Teaches You. Today we are going to do the IB Physics chapter Motion in an Electromagnetic Field. We are going to do the fourth video of this chapter. It is going to be a D3 section, fourth video. Okay, so in the yesterday's class, we had done till this portion. We had done why, what causes the electron or the charged particle in a magnetic field to behave and go in a circular path. That's what we had discussed in the previous class. So we are going to do some questions today regarding this. Okay, the first question that we have is an electron is moving in a uniform magnetic field. Okay, uniform magnetic field has been given to us. The velocity of the electron is perpendicular to the magnetic field. Very good. So when it is perpendicular to the magnetic field, instead of getting a helical path, you will get a circular path. Okay, so what are they given us? They have given us the speed, and the magnetic field strength is 1.2 millitesla. Okay, so we don't know we don't remember the formula. Okay, let's see what happens. We know that QVB is equal to mv squared upon r. Therefore, V and V gets cancelled. Therefore, QB is equal to mv upon r, or r is equal to mv upon QB. Right? So, since it's an electron, we can say is equal to mv upon EB, where m is also going to be the mass of the electron. Okay, so what have they asked us in the beginning? They have asked us explain why the kinetic energy of the electron does not change. Okay, why does the kinetic energy not change? Because the velocity is not changing. The velocity is not changing because the magnetic force that is being acted upon the particle is perpendicular to it. Because the basically the direction is perpendicular, we say that there is no work being done. No work being done, therefore the velocity remains the same. Therefore, the kinetic energy of the particle will remain the same. Always it's going to be the same. Understood? That's what they have written here. See, the magnetic force on the electron is always perpendicular. It's always perpendicular to the electron's velocity. So the magnetic field does not do any work on the electron. The change in kinetic energy is equal to the work done. Hence, it is zero. There is zero amount of work done. So there is going to be zero change in kinetic energy. I hope you understood this. Okay, let's move on. Next, calculate the radius of the circular path of the electron. So we know the mass of the electron, we know the velocity of the electron, we know the charge of the electron, we know the magnetic field on which the electron is traveling. Everything is known. So all we have to do is put the formulas here, put the values here, and then we will get 3.1 centimeters. Any doubts here? Okay, next, calculate the period of motion. So what is the meaning of period of motion? Okay, the period of motion refers to the time it takes an electron to complete one revolution. Okay, so it is moving in a circular path. So how much time is it going to take to complete one revolution? It is a very easy concept. Now, for a circular motion, we know that velocity is equal to 2 pi r upon t, that is time period, the time taken to complete one revolution is and upon the total distance covered by the particle. Okay, this is nothing but distance upon time. Okay, it is just a distance upon time formula. 2 pi r is the circumference of the circle in which the electron is revolving. So we can say that time period is equal to 2 pi r upon v. Am I right? Time period becomes equal to 2 pi r upon v. Now, we know the value of r. We just calculated it to be 3.1 centimeters. So, 2 into pi into 0.031 upon the velocity, that is 6.5 into 10 raised to power 6. You will get 3 into 10 to the power minus 8 seconds. Any doubts here? Okay, let's move on. The magnetic field is so adjusted that the radius of the path is 4 centimeters. calculate the magnetic field strength after the adjustment. Now, actually, I'm going to ask you a simple question. Okay, how is the radius in the magnetic field affected? Now, look at the formula for radius. R is equal to mass into velocity upon q into b, right? So, can I say that the radius is inversely proportional to my magnetic field? So, exactly. Very good. So the magnetic field has to be lower, right? That is one thing. So when you're so the why is it important to know the theory? Because when you're doing your calculations, you should know that you should know that the value should always come less than the original value. If you are getting some value greater than the original value, original magnetic field, then you can assess yourself and say that you have made a careless mistake. Okay, so we know that basically radius radius is equal to mv upon qb. So the radius is now 4 centimeters. That is 0.04 centimeters, 0.04 meters. So the magnetic field is equal to mv upon rq. Okay, we know the mass, we know the velocity, we know the uh, radius, and we know the charge. Okay, so the mass is how much? 9.1 into 10 to the power minus 31 kgs. The velocity is how much? 6.5 into 10 to the power 6 meters per second. Then you have the charge, 1.6 into 10 raised to the power minus 19 coulombs. And finally, the radius is 0.04 meters. Okay, so at the end, you will get what? 0.93 millitesla. That will be the final answer. Clear? Okay, let's do a practice question here. Okay, now in the practice question, it is said that a charged particle of mass m moves in a circular path in a region of uniform magnetic field B that is directed into the plane. That is, the magnetic field is going inside the plane of the paper. Okay, the radius of the path is r and the speed of the velocity particle is v. Oh, I think we just have to derive a formula. That is great. State the sign of the charged particle. Okay, now the magnetic, use your left hand. Keep your left hand above. Now, the magnetic field is downwards. So, the magnetic field is downwards. Now, we know that the force, you see the red dot here? This red dot? Keep your keep your index finger pointed downwards on this red dot. Okay, and then what do? You see that the force is acting inwards, right? Then and only then what will happen? If the force is acting inwards, then and only then it will move in a circular path. So then you have to curl your thumb like this. Okay, you curl your thumb like this in the inward direction of the field. Okay, and then what do you do? What else? What else can you do? The current is in the upward direction, right? The current is basically in the upward direction. So if we consider the charge to be positive, is it a positive charge? Have they given us whether it's a positive charge or not? No, they haven't given us whether the charge is positive. So we can write our answer in such a way. If the charge is positive, then the charge is moving in an anti-clockwise direction. If the charge is negative, that is, if it is an electron, then it is moving in a clockwise direction. Understood? So, the first answer is this. State the sign of the charged particle. The charged part is positive. Okay, clear? Because see, the velocity is here in this direction. So, the charged particle has to be positive because the charged particle has to rotate in the anti-clockwise direction for our situation to resolve. Clear? One second. In your screen, the dot is where we have to put our index finger. We keep the index finger like this. Okay. Then we rotate our thumb towards the inner direction because the centripetal force is inwards. So this thing, the middle finger basically points upwards, right? The middle finger points upwards. Now, the velocity is also pointing upwards, the middle finger is also pointing upwards. Then what does it mean? It means, see, current has to go in the clockwise direction. The current has to flow in the anti-clockwise direction. The particle is rotating in the anti-clockwise direction. If you see the velocity, it's here, right? So it's both of them are revolving in the anti-clockwise direction. That is only possible if the charged particle is positive. Okay, because if the charged particle were to be negative, then what would have happened? The charged particle would have had to rotate in the clockwise direction to make the current anti-clockwise. Right? To make the current anti-clockwise, the charged particle would have had to travel in the clockwise direction if it were negatively charged. Clear? That is what I'm trying to tell. Next. Next. Determine in terms of mass, the magnetic field, the radius and the velocity, the magnitude of the charged particle, the magnitude of charge on the particle. So we know that R is equal to mv upon qb, right? Therefore, your q will be mv upon rb. That's it, finished. That's the answer, right? Okay. Now, question number 8. The speed of a particle in question number 7 and the magnetic field strength are both doubled. Okay, speed has been doubled and the magnetic field strength has been doubled. What is the radius of the path of the particle after the change? It does not change because the charge, see, basically the speed is at the top. R is equal to mv upon qb. In the numerator also you have doubled it, in the denominator also you have doubled it. So the double gets cancelled. So what happens? You are left with the same radius r. Clear? Same answer? Okay. Next, in alpha particle, what is an alpha particle, Akshay? Helium 2 plus. You have a helium atom here. Helium has two protons, two electrons, and two neutrons. Okay, it has two protons, two electrons, and two neutrons. Now, if you're going to remove the electron, okay, if you somehow remove the electron, then what is going to happen? Both the electrons, if you remove them, you get an helium 2 plus. That is what an alpha particle is. Okay, so an alpha particle, charge 2 plus, mass has been given to you, is moving in a circular path in a uniform magnetic field of magnitude 0.8 teslas. Calculate the radius of the path when the velocity of the particle is 7.5 into 10 to the power 5 meters per second. So again, we'll use the same formula. R is equal to mass of an alpha particle. Alpha particle looks like this. Okay, alpha particle is alpha, mass of the alpha particle multiplied by velocity of the alpha particle upon the charge of the alpha particle and the magnetic field. So mass of the alpha particle is 6.64 into 10 to the power of minus 27 multiplied by the velocity is how much? 7.5 into 10 to the power 5. 7.5 into 10 to the power of 5 upon your what is it? Charge is at 2 into 1.6 into 10 to the power minus 19 multiplied by b is, calculate the b, 0.8. Okay, so if we solve this, okay, let's see, let's actually try, let me just make a guess. So this will become what? Okay, 6. Can I say 0? See, Akshay, can I say that 0.8 multiplied by 2 is how much? 1.6. Okay, now 1.6 into 6.64 is how much? So basically by the 16 or let's say the table of 16. 16 fives are how much? 80. 16 fives are 80. 16 fours are 64. Okay, 16 fours are 64. So approximately I can do this. 6, this and this I can cut off. Okay, this will become 4. I'm just giving a rough calculation. You do that in the calculator much more easy. Now 4 0.4s are 16. Okay, now you are left with 10 to the power minus 27 plus 10 to the power 19 is how much? 27 minus 27 plus 19 becomes minus 27 minus 17. Uh, what? Minus 8, exactly. Minus 8 plus 5 is how much? Minus 3. So 10 to the power of minus 3, and then you have 7.5 upon 0.4 into. Now you can again make some assumptions and say that this is 75 upon 4. This is not an assumption, but 4 ones are 4 twos are 4 ones are 4, 5 6 7, 4 4 nines are 36. Somewhere around 19 into 10 to the power of minus 3, or 1.9 into 10 to the power of minus 4, or simply 190 centimeters. What is the answer? 1.9 into 10 to the power? Oh, yeah, 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 sorry. So, no, 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 I made a mistake. It's not 1, it's going to be 1.9 into 10 to the power minus 2. Yeah, because the decimal is going towards the left, so it is going to be 1.9 into 10 to the power minus 2. That is correct. Here, okay, 1.9 centimeters, exactly. 1.9 centimeters. I made a mistake. Okay, now the velocity of the particle when the radius of the path is 2.5. Now we know that R is equal to mv upon qb. Therefore, v is equal to r q b upon m. Okay, so radius is how much? 2.5, right? So 2.5 into 10 to the power minus 2 multiplied by the whole thing, 2 into 1.6 into 10 to the power minus 19 into 0.8 upon 1.6 into 10, sorry, yeah, no, 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 no. The mass is how much? 6.6, right? 6.64 into 10 to the power of minus 27. Yes, minus 27. So now what do we get? We have to find the velocity. Again, we will do some rough calculations. So I'm going to do this 2 and this 0.8. I'm going to cut this as uh, 4. Okay, I'm going to cut this 4 and this 1.6 as 0.4. Okay, so 25 into 0.4 is how much? 25 into 4s are 100. 2.5 into 0.4 is 1, right? Sorry, 2.5 into 4 is 10. 2.5 into 0.4 is 1. Yes, 1. Now 10 to the power minus 2 into 10 to the power minus 19 is how much? 10 to the power minus 21. My plus 10 to the power 27 will give you how much? 10 to the power of 6. So 1 into 10 to the power of 6 meters per second. What is the answer? Yeah. So basically they have 9.6 into 10 to the power of 5. I have made rough calculations and I am almost close to them. I can write this as 10 into 10 to the power of 5 meters per second. So see, without using a calculator, you are just approximating. That's how Indian students do it. Okay, we don't see in IIT exams and all, we don't have a calculator. We have never had a calculator. So basically, this is what we are trained to do from the very beginning. We don't have time to do these detailed calculations, so we just have an approximate value. Okay, and once we have the value, we have the four options in front of us. We will choose the most accurate or most similar option in the exam. Okay, so let's. Did you understand these three questions? Any problem? Okay, shall we move on to the next one? Okay. Oh, is this going to be the owl drop experiment? No, no, no. Okay, fine. So, determine the charge to mass ratio for a charged particle. Okay, now let's see. The ratio charge upon mass for a charged particle can be determined by making the measurements of the charged particle's path in a uniform magnetic field. To show how the method works, okay, to show how the method works, take the example take the example of measurement of a charge per unit mass of an electron. This quantity is also known as the specific charge of an electron. A beam of electrons is fired through the gas using a hydrogen or a helium using the equipments shown in figure 13. The gas is at a very low pressure. So we have to calculate the charge to mass of a particle. Okay. Now what have we taken here? We have taken a gas, basically very low pressure of gas, and that is we are taking a helium gas here. Now, this gas is at very low pressure so that the electrons do not collide with too many gas atoms and lose too much energy. So, why do we take gases at low pressure? Because if they are placed in a magnetic field, then what ends up happening? They can get energy, right? They, because a force is being experienced on them, so they could get energy in them. Now what is going to happen if they get energy? They will start to collide. If they collide, they will reduce the overall kinetic energy, or the energy becomes reduced. They will lose too much energy. When a uniform magnetic field is applied at right angles to the beam direction, yeah, the electrons move in a circular path, and their path is shown by the emission of visible light from atoms that have been excited by the collision with electrons along the path. Okay, so what is happening here? So one second. So what have we done? We have fired a beam of electrons in the gaseous helium. Okay, now hit when the electrons hit on the helium atoms, what ends up happening? They transfer some energy from the electron to the helium atom. Thus, the helium atom's electrons get excited. Now, when an electron gets excited, it goes to a higher energy level. Okay, so in an atom, the electrons are usually present in their orbit. Okay, but when the electron gains some higher energy from the outside, it gets excited to a higher energy level. Now when this electron wants to release its energy and come back to the original state, what ends up happening? It cannot take the energy that it gained with itself to come down. So what does it do? It basically releases the excess energy in the form of light radiation. Okay, and that light radiation is visible to our naked eyes. So what can we see? We can actually see the pathway taken by the electron. We cannot physically see the electron, but we do see the light that is being emitted by the collision of an electron with a helium atom. Therefore we are able to see the radius of the electron. We can now measure the radius of the electron. That's how we do it. Okay, now the kinetic energy of an electron or any charged particle moving this way can be regarded as a constant in uniform magnetic field, because the magnetic field is perpendicular to the electron's velocity and no energy is transferred. So the velocity of the electron is going to remain the same when it is moving in a circular path, because work done is zero. Now, the electrons of mass me are accelerated using a potential difference of v before entering the field. Okay, now how do you provide an electron with some amount of velocity? You by accelerate it, right? Initially the electron was it in the rest position. Now I'll give you a simple example. When you are driving a car, okay, you want to drive the car at 50 kilometers per hour, okay, but do you start by actually having 50 kilometers per hour of speed? No, you are at rest, your car is at rest, you are at 0 kilometers per hour, okay, your velocity is zero. Okay, now you have to accelerate yourself by burning some oil. Okay, by burning the petrol you are accelerating yourself into 50 kilometers per hour, and then afterwards, to maintain your car in 50 kilometers per hour, you don't have to accelerate anymore. Once you have reached the velocity, that's it, you are good. Afterwards, when the car is moving, it is not accelerating. So here we are doing the same thing. We have a potential difference. Okay, so we have a potential difference v, in which we have managed to accelerate the electron from rest to a certain velocity v before allowing it to enter the magnetic field. Okay, we are giving it some velocity and then we are sending it inside the magnetic field in the perpendicular direction. Are you able to imagine this now? Okay, now, so their energy is half mev square. We also know this. Half mv square is the energy of kinetic. Now, is equal to ev. So what is the kinetic energy that the electron had in the end? It is going to be equal to the potential energy that it gained from the potential difference. Okay, so the amount of, see, that's the same thing that is happening here, right? When you drop a ball from a certain height, what is happening? The potential energy that you had in the beginning is coming out to be the kinetic energy downwards, right? The same thing is happening here. So you accelerated the electron through a potential difference, okay, and that potential difference is giving it some kinetic energy as it enters into the field. As it enters into the field, you are providing it with some kinetic energy. Am I right? Okay, now what you have to see, you have to see that your half mv square is equal to ev. Okay, so v becomes equal to root under 2, no, let's actually derive it. So you have half me, mass of an electron, v square is equal to ev. Therefore, your v square is equal to 2 ev upon, this v should not have a curl because it's voltage, potential difference, upon me. Therefore, v is equal to root under 2 ev, oh again, v, oh, v upon m. E. This is how you are getting the formula. Clear? Next. Now, using V is equal to RBE upon M. We know that, so we know R is equal to MV upon QB. Therefore, V is equal to R into Q into B upon M. We have this formula is the velocity from the centripetal acceleration proof earlier. So when we equate these two, what do we get? Huh? Now we are going to use this velocity. Okay, we know velocity is equal to root under 2 mev upon me. Now we have this also. So what do we do here? We will equate both of them. So v v is equal to your r b e upon me. Okay. This is also equal to root under 2 EV upon, oh, I'll leave it. This, I'll just write it like this. It's a habit. I don't know what to do. Okay, so you are squaring on both sides. So you'll have R square B square E square upon ME square is equal to 2 EV upon ME. This gets cancelled. The square is gone. Now, your voltage is here. Okay, so electron gone. So what are you left with? You need to find the charge to mass, right? So charge is E upon ME is equal to what? 2 into V upon R squared B squared. That's how you get your formula. Understood? Clear? So this is known as the charge to mass ratio. Now, this is of historical importance to physics. This is of historical importance to physics because even though J.J. Thomson identified the electron, this measurement of specific charge was the best the physicist could do to measure the properties of a particle until Millikan determined the electronic charge. So Millikan's oil drop experiment, the contribution that JJ, you know who JJ Thomson is, right? He is the discoverer of the electron. So JJ Thomson discovered the electron, but he was not able to calculate the charge of an electron. Okay, he was only able to calculate the charge to mass ratio. Okay, that is charge upon coulomb upon kg. Coulomb per kg is all he could find. But what ended up happening was Millikan, a great physicist, Millikan did the oil drop experiment and he was able to definitively calculate the charge on a single electron, and that single electron was coming out to be 1.6 into 10 raised to power minus 19 coulombs, and because of that people were able to declare the mass to be 9.1 into 10 to the power minus 31 kgs. So everything is connected, every single thing is connected from one to another. Okay, next, for the general case, when a particle of mass m with a charge q has been accelerated through a potential difference v in a uniform magnetic field, the strength b and moves in a circle radius, and the equation becomes q upon m is equal to 2v upon r square b square. Okay, so if you don't have an electron but a charged particle, so instead of writing E you will write Q. That is the only difference that we are doing here. Okay, I hope this concept is extremely clear to you. Okay, let's move on. Now, worked example number 8. So in an experiment to determine the specific charge of an electron, a student using a beam of electrons accelerated from rest through a potential difference V. The electron enters a region of uniform magnetic field V and the radius of their circular path is measured. Now, the student varies V. Okay, he's varying V for each value of V and adjusts V until the radius of the path is 4 centimeters. Wait, छोड़ दे. So the graph shows the value of p square plotted against v and the line of best fit. Okay, estimate the gradient of the line of best fit. Gradient. Gradient means this thing only, no? The tan theta. Gradient is nothing but tan theta. So you can say that tan theta will be equal to how much? 2.9. This line is 2.9, right? The end line. That is going to give you 2.9 into 10 to the power minus 6 upon 400. So this is what gradient means. Gradient means the slope, and the slope is always equal to tan theta. For any type of formula that you have, the gradient is going to be tan theta. Okay, so that's what they have done here. So they're it's coming out to be this value 7.25 into 10 to the power minus 9 Tesla per volt. Now Hence, determine the specific charge E upon m of the electron. Okay, so E upon m value is how much? We know that E upon mass of an electron is equal to 2V upon B squared R squared. Okay, but we have already calculated B squared upon R squared, right? Sorry, no, wait. We know the value of B squared upon V. We know this value. It is coming out to be 7.25. Am I right? 7.25 into 10 to the power minus 9. So, okay, what else do I need? Have they given us the radius? 4 centimeters. Okay, now I know the value of B squared upon V squared. So E upon mass of an electron is equal to 2 upon 7.25 into 10 to the power minus 9, because B square upon V is that much, into radius square, that is 0.04 the whole squared. Now E upon ME, are you able to follow me? See, basically B square upon V, right? If you have, see, if A upon B is equal to 2, then B upon A is equal to 1 upon 2, right? That's all I have done. Okay, did you understand? See, we knew the value of B square upon V, so I just placed the B square upon V value at the bottom, so that I would able to do this. Okay, so is equal to 2 upon 7.75 into 10 to the power minus 9 multiplied by 4 square into 10 to the power minus 4. Am I right? Because I can write 4 into 10 raised to the power minus, sorry, uh, 4 into 10 raised to the power minus 2 is the radius. Therefore, the square will become 4 square into 10 raised to the power minus 4. Okay, so E upon ME is equal to 2 upon 7.75. Now, 10 to the power minus 9 into 10 to the power minus 4 is equal to 10 to the power minus 13 plus 2 is equal to 10 to the power minus 11. So, I can bring it up and say 10 to the power 11. Okay, and this is what, to 4. Now, this 4 into 4. So this 2 and this 4 will get cancelled and I'll get 2. So 7.75 into 2 is how much? 7.5 into 2 is 15. So 7.75 into 2 is 15.5. Right? So minus, oh, sorry. Minus 9 minus 4. No, wait. Minus 9 minus 4 is how much? Minus 13. Plus, oh, wait. Yeah. I'm sorry. It should be 10 to the power 13. Yeah, you're correct. It should be 10 to the power of 13. So, 15.5 into 4, 15 fours are 60, 5 fours are 20, 60, 60, 60. Should it be 62? You just check. Now, can you find me the final answer? 1.61. Are you sure it's 1.61? No, it's because their answer is coming out to be 1.72. What is the mistake that we did? Oh my god, yeah, yeah, I got it, got it. It should be 7.25. My mistake. So this will become 7.25. So basically, this whole thing will be 7. So 7.25 into this thing. So I'll get 7.25 into 4 into 4. This will become 2. 7.25 into 2 is 15. 15 into 4 is 60. It should be 60 at the bottom, not 62. So now the correct answer is how much? Is it coming out to be 1.72? Okay. This is how you will be able to solve it. Okay. Understood. You don't have to do what they're doing. See, these people, they want to make the b square upon b. But why do you have to make unnecessary steps? Right? You can simply write it like this itself. You don't need these unnecessary steps to actually help you understand. So you can just see a upon b is equal to 2, therefore b upon a is equal to 1 upon 2. That's it, finished. Next, charge moving in a perpendicular magnetic and electric field. Now what is going to happen? Charge moving through charge moving in a uniform magnetic field to a circular orbit. Movement in a uniform electric field leads to a parabolic trajectory. We know this, right? S is inverse is directly proportional to x square. So basically, you will get a parabolic pathway. However, it is possible to combine the fields in a particular way to do a useful job. The trick is to combine the magnetic and electric field at right angles to each other. As before, this analogy ignores the negligible effect of gravity on the charged particle. Okay, gravity is so small that we can consider it to be negligible for all intents and purposes. Understood? Okay. Now, for the arrangement shown in figure 14, the electric force Fe is vertically downwards. The electric force is coming out to be downwards, and the magnetic force Fb is, the electrical force is vertically upwards. Why is the electric force upwards? Because you have an electron here. Okay, an electron is coming like this, it will get attracted towards the positive plate. Right, see, because the electric field is where it's from top to bottom. The electric field is from top to bottom. Now, if it is from top to bottom, then the upper plate will be positive. The upper plate will be positive. So, electron when it enters the this electric and magnetic field, it will start moving in the upward direction. So, what is going to happen? The Fe is vertically upwards. The electric force is vertically upwards, and the magnetic force. Now, look at this. Here, the magnetic field is perpendicular to the electric field, and it is inside the plane of the paper. Okay. Now, use your left hand. Okay. Now, and do this. The magnetic field is inside. Okay. The movement is here. Okay. The movement is from where to where? The current, if the electron is moving this side, then see, look at this one here. So the magnetic field is downwards. Okay, the current is going to be in the opposite direction of the electron, like this. Now, where does the thumb point? Towards me, right? Yeah. Therefore, the magnetic field force will be downwards. So both of them are acting opposite to each other. The electric as well as the magnetic field are creating a force on that small electron. One is in the upward direction, the other is in the downward direction. For the arrangement shown in figure, the electric force Fe is vertically upwards and the magnetic force Fp is downwards. When these forces are equal and opposite, there is no net force acting on the charged particle. No net force, zero net force happens. Now, for this to be the case, Fe is equal to Fp. So the force due to the electric field should be equal to the force due to the magnetic field. Now both of them have q values, right? Can I cancel them both? Right, I can cancel these q and q values, so I'll be left with what? I'll be left with E is equal to VB, right? Therefore V is equal to E upon B. Clear? Okay, so next, using the results from earlier in this topic and from topic D2, this leads to V is equal to E upon B. For a particular ratio of E upon B, there is a unique speed at which the forces will be balanced. The charged particles traveling more slowly than this speed will have a smaller magnetic force, while the electric force is unchanged. The net force will be upwards on the diagram. For faster electrons, the magnetic force will be larger and the electron will be deflected downwards. This provides a way to filter the speed of a charged particle, and the arrangement is known as the velocity selector. So if you have a higher velocity, then you will have a higher magnetic field and the electron will go downwards. Okay, higher velocity means what? Higher velocity, that's what they're trying to say, no? So higher velocity means the magnetic force acting on the charged particle will be more, so you'll have a downward force like this. For a lesser velocity, the what will happen? The electric force will win. Therefore the electric force will make the electron or the charged particle move in the upward direction. This provides a way to filter the speed of the charged particle, and the arrangement is known as the velocity selector. Okay, clearly, did you understand this? So this is how you are able to differentiate what the speed of the charged particle. Understood? Because you will always know what the value of electric and magnetic field is going to be, because you're the one who is generating this electrical and magnetic field, right? So you know the strength of the field, and if you know the charge, there is no need of the charge. You can calculate the velocity through this. Okay, now an electron enters a region of crossed electric and magnetic fields. The fields are perpendicular to each other and to the electron's velocity. The electron travels undeflected through the field. What does it mean? Undeflected means it is moving straight through the field, right? Undeflected means it is moving straight through the field. So to make the electrons move in a straight line, so your electron will start moving in a straight line if your electric and magnetic field are equally balanced. Okay, if they remain equally balanced, you will get a straight line. Okay, now what do we have to do here? Okay, so the magnetic field strength is 50 millitesla. The calculate the velocity of the electron when the electric field strength is 7.5 kilowatts. So it's very easy. We know that velocity is equal to how much? Your electric field upon magnetic field, right? Electric field upon magnetic field. Electric field has been given to you. Okay, 7.5 into 10 to the power of 3. 7.5 into 10 to the power of 3 upon your magnetic field is 50 into 10 to the power of minus 3. So when this goes up, you will get 7.5 into 10 to the power of 3 into 10 to the power of 3 upon 50. So 25, 0.3s are 77.5, 25 into 2s are 50. So this will become 3 upon 2 into 10 to the power of 5, or 1.5 into 10 to the power of 5. That's how you'll get this. Clear? Next, then you need to calculate what? You need to calculate your um, the electric field strength when the velocity of the electron is 2.4 into 10 raised to power 4 meters per second. Okay, we have the velocity, we have the this thing, so we know that V is E is equal to VB is equal to 2.4 into 10 to the power of 4 multiplied by 50 into 10 to the power of minus 3. So what will we get? 10 to the power 4 into 10 to the power minus 3 is 10. 24 into 5s are 20, basically 20, 2 into 5s are 10, 100. 4 into 4 into 5s are 20. So you will get 24 into 5s are 120. Okay, 120 into 10 is equal to 1200 is equal to 1.2 into 10 to the power of 3 volt per meter. Clear? Okay, next. Okay, the brain bridge mass spectrometer is a good. Okay, let's actually discuss this. Okay, the brain bridge mass spectrometer is a good example of a number of aspects of electric and magnetic fields being through brought together to perform a useful job. There are two parts of this instrument: a velocity selector with electric and magnetic fields at right angles to each other, deflection chamber with only a magnetic field in this diagram in the paper. It is left as an exercise for you to show that identical charged ions of the same speed but different mass travel in circles of different radii in the deflection chamber. The ions arrive at the photographic plate or the electronic sensor at different positions. These are the electronic sensors, okay? The photographic plate or the electronic sensor. This is what they're talking about, okay? At different positions. Their mass and relative abundance can be determined. So this is the deflection chamber. This is the velocity selector means what? By using the electric and magnetic field here. Can you see this? By using the electrical and magnetic field, you are giving this electron or any charge that you have a certain velocity. A certain required velocity is given using this. Okay. Now, depending on the mass of the charge, you can have different radii. Understood? So this is the whole magnetic field chamber. This is where the deflection is actually happening. Okay, understood this? Oh, so this is the acceleration, this is the velocity production chamber. Okay, this is the velocity selector, and the other one is the deflection chamber. The velocity selector has both electric and magnetic fields. The electric fields are provided by these two plates. Okay, this plate here and this plate here is the one that is providing the electric field. And you can see that the magnetic field is going inside the plane of the paper. So electric field is going downwards, the magnetic field is going like this. Both of them are perpendicular to each other, so therefore you have a velocity selector. Okay, by manipulating the electric and magnetic fields, you can have a certain amount of velocity. We know this, right? We have just done a question on this. Now, you are bringing it into the chamber where there is only magnetic field. And when you have a magnetic field and the charge is entering at right angles to the magnetic field, what type of path will you get? You will get a circular path. Problem? Okay, you will get a circular path. Okay, now, next. Measurements. As it's so often the case, what was originally complex? What was originally complex and expensive technology can be improved and refined over time, making it cheaper, more reliable, more compact, and more useful. In the case of mass spectroscope, as well as being used for analytical chemistry. It can analyze isotopes for dating samples in carbon dating. Mars spectrometer has been sent to Mars and to Saturn's moon Titan to analyze the surface sample. Okay, so what it does is basically it takes in some soil, okay, and that Mars spectrometer allows us to calculate the mass of various different samples in that mud or in that soil. Okay, so this because we know that different elements have different masses. Different elements have different masses, so basically that mass spectrometer allows us to identify what all elements are present on that surface without actually viewing it, without actually going there and seeing it. You have the ability to check what all materials could be present in that soil. Now recent developments now enable a mass spectrometer to provide rapid analysis of body tissue. The onco knife or the eye knife can determine whether the tissue is cancerous or not. This informs the surgeon in real time during an operation, making the procedure quicker and more accurate. Okay, so you have a knife like this, and the knife basically scans whether the tissue is cancerous or not. So basically, in the whole patient's body, that surgeon is able to correctly visualize which is a cancerous tissue that has to be removed and which is a healthy tissue that has to be kept inside the body. Understood? Okay. Now, uh, how many pages are left now? Okay, only two more pages left. Ions of mass 1.5 into 10 to the power minus 26 kg and charge plus E are accelerated from rest through a potential difference of 600 volts. The ions enter a region of cross electric and magnetic fields. The magnetic field strength is 0.25 Tesla. Calculate the speed of the ions. Okay, you have to calculate the speed of your ion. Now, how will you do this? E upon m. Okay. Now, but calculate the speed of the ions. It's easy. It's easy. It's easy. See, we can find the electric field. So, electric field is what? Electric field is equal to charge multiplied by potential difference. Okay, the charge is plus E is equal to 1.6 into 10 to the power minus 19 multiplied by 600. So basically 9.6 into 10 to the power minus 17. Right. This is the electric field. One second. So in this question, they have what ion of mass 1.5 into 10 raised to minus 26 kg and charge of plus E are accelerated from rest through a potential difference of 600 volts. The ions enter a region of cross electric and magnetic fields. The magnetic field strength is 0.25 Tesla. Calculate the speed of the ions. Now, how do you solve this question? We have been given the mass of the charge, and then you know that charge is equal to mass of the charge is 1.5 1.5 into 10 to the power of minus 26. Then you have charge is equal to 1.6 into 10 to the power minus 19. Then you have potential difference is equal to 600 volts. 600 volts. Then the magnetic field is equal to 0.25 Tesla. Now we need to calculate the speed, question mark. So do you know, remember this formula? Basically potential energy is equal to kinetic energy. Okay, potential energy is equal to kinetic energy. Potential energy is for what? Potential energy is equal to Q multiplied by V is equal to half me v squared, right? So this Q is 1.6 into 10 to the power minus 19 multiplied by 600 is equal to half. Mass is how much? 1.5 into 10 to the power minus 26 into v squared. So this will become 9.6 into 10 to the power minus 17 into 2 upon 1.5 is equal to v squared. Okay. Got it? Okay. So see, potential energy, that was the potential energy is being equated to kinetic energy. Clear? Potential energy and kinetic energy you have equated. Now QV is equal to half MEV square. Okay. Now V is equal to how much? Root under this value. 9.6 into 10 to the power minus 17 into 2 upon, this should be 1.5 into 10 to the power minus 26 upon 1.5 into 10 to the power minus 26. So basically 0.5, 3 into 0.5 is 1.5, 3 threes are 9 and 3 2. Okay, so 3.2 into 2 is 6.4, right? Is equal to root under 6.4 into 10 to the power minus 17 plus 26 is how much? 17. 10 to the power 9. 10 to the power of 9 upon 0.5 is equal to root under 64 upon 5 into 10 to the power of 9. Okay, so what will we get? Uh, we can if I take 640, no, I can take this 8 out, right? 8 into root under, I can write 10 into 10 to the power of 8 upon 5. This will also get cut off 2. So I'll be left with 8 root 2 into root under 10 to the power, it becomes 10 to the power of 4 meters per second. Correct? Okay. So 8 root 2 is how much? 1.414. 8 into 1.414 into 10 to the power of 4 meters per second. Can you tell me what is the value? 1.13 times 10 to the power of 4 meters. No, 10 to the power 5, right? What is 8 into 1.414? 11.3 times 10 to the power 4 meters per second. Is this the correct answer? Okay, fine. Did you understand this question? We were moving in the wrong direction in the beginning. So we were supposed to equate the potential energy and the kinetic energy. Next, given that the net force on the ions is zero, calculate the electric field strength. If the net force is zero, what does it mean? We can say that V is equal to what? E upon B, or E is equal to VB. Okay, so electric field is equal to 11.3 into 10 to the power of 4 multiplied by what is the magnetic field? 0.25. 0.25. What is the answer I'm getting? See, I can write 0.25 as 1 by 4. 11.3 if I equate it to 12, I should get somewhere around 3 into 10 to the power 4 volt per meter. Is it somewhere close? Yeah. So basically, you have using a calculator, using a calculator. What are you getting? 28,250. Approximately, I got 30000. Okay. they are approximately the same. Okay, so Akshay, can we do one thing? Can we stop the class here and can we continue this in tomorrow's class? We will start with D4 also. Okay, Sherida. Okay, just hold on one second. Now, students, if you really like my videos, please do like, share, and subscribe. I'm gonna bring more videos on the IB physics section as soon as possible. Okay, we will start with the, I think, E in the next few days. Okay, so I'll see you in the next class. Thank you so much.